All right, so let's talk about delta G and equilibrium. So I already talked about this a little bit, but delta G is really the kind of why behind equilibrium, whereas equilibrium is kind of the what. You know, how much product are you going to get is equilibrium. Why are you going to get that much product is kind of the delta G thermodynamic look at it. So if we think about A and B in equilibrium with one another, we can say if delta G is positive, negative, or 0, right? Those are the options for the value of delta G. So if delta G is positive, then it's non-spontaneous. And not only is it non-spontaneous, it's actually going to be spontaneous in the opposite direction. And so what that means is that you're actually going to have here B turning into A. If it's positive, or if it's negative, then it is spontaneous, right? So you're going to have A turning into B. And then if you're talking about 0, you're at equilibrium. So it looks like nothing is happening because A and B are at equilibrium, right? One is turning to the other just as quickly as B is turning into A. All right, so that's the delta G possibilities. Next up, let's take a look at the equilibrium possibilities, right? And so if you think back to equilibrium, we compared Q and K in terms of Q is where you're at during the reaction, K is where you're going to end up at the end of the reaction, right? So you can say Q is greater than K, Q is less than K, or Q is equal to K. So if Q is less than K, then Q is going to go towards K. Q always goes towards K because Q is where you're at in the reaction. K is where you're going to end up. So Q must shrink so that these two values are equal. And so in order for that to happen, B is going to turn into A. And you can see this is the same thing that happens up here. Next up, Q is less than K. Here, Q's got to grow to become K, so that way they're equal. And so you're going to have A turning into B, which is exactly what you have up here. And then if you have Q equals K, you're at equilibrium. Right, and so here you're just going to be at equilibrium, right? A and B are transforming to each other at the same rate, right? And that's what you have right here, right? So you can really think about delta G right here as the kind of Y. These values are what they are in terms of energy levels, and then Q and K is what they are, is the what. Okay, this reaction forms mostly product. This reaction forms mostly reactant, that kind of thing. So one of the big issues, though, is so far we haven't really taken a look at delta G. We've only taken a look at delta G under standard state conditions. And so we're not always at standard state. And so it's not that useful, or it is useful because we can turn it into non-standard states, right? So let's take a look at that and see how K and Q play a role in that. And so the overall equation is that the delta G of the reaction, not at standard state, is equal to the delta G of the reaction at standard states plus RT ln Q, right? So you can see Q equilibrium, it's right there, equilibrium, where we're at in the reaction, Q right there, it's going to play a role in what our current value of delta G is. So let's just define this. This is delta G at non-standard states. This is delta G at standard state. This is the gas constant. And it's the energy one. We're talking about energy, so 8.314 joules per mole Kelvin. This is the temperature. And of course, it needs to be in Kelvin. So yet another K. I'll write out Kelvin. Lots of Ks. Next up, ln is natural log. So think back to math class, log base E, natural log, whatever you want to do it. There's a button on your calculator, but it's good to know what it means as well, but we won't cover that. And then finally, Q here is the reaction quotient, right? And reaction quotient, it's always the same thing, products over reactants. Right, so equals products to some exponent over reactants to some other exponent. Cool. So you can see they're directly related. They're essentially the same kind of, talking about the same concept just in different ways. So let's take a look how we can apply this equation to get some stuff done. So maybe one of the questions we can ask ourselves is, will water evaporate? Right, you've got a puddle of water. Will it evaporate? And so that depends on the conditions. So let's take a look. So H2O as a liquid, going to H2O as a gas, right? Water's evaporating. We can look at the delta G of this. At the standard state, you're at 8.59 kilojoules per mole. And then you can also look at the Kp of this. Kp is going to be 0.0313. So at equilibrium, this is how much product over reactant you have. And then if we think about what the value of Q here, Q is always going to be some products over reactants to some exponents. And then remember, we ignore any liquids, right? So we're going to kind of ignore this guy right here in our reaction quotient. So it's actually just related to the concentration of H2O as a gas. So there's different scenarios we can look at. Let's look at the first scenario, and that's at standard state. So, right, remember this delta G right here, it's got this little degree sign, which means that it's at standard state. And you can tell right away this number is positive, so you can tell right away that it's not going to be spontaneous at standard state. But let's take a look at the math in it and find out how it all works. So standard state for a gas, you're assuming that the gas is at 1 atmosphere, right? All the gases are at 1 atmosphere, so you're assuming 1 atmosphere of water. 1 atmosphere of water is quite a bit, and so you can think of this as, you know, if you have a water bottle that's closed, some of it will turn into gas, and then it'll just kind of stay there. More is not going to evaporate. So we can see that Q right here is essentially just equal to the amount of gas, right? So Q is essentially just equal to the amount of water in a gas. And we just said that was 1 atmosphere, so Q is essentially just equal to 1. Q is equal to 1. And so just from that, you know, Q is greater than K, so Q must shrink. So the gas is actually going to turn into a liquid. Right, so you can figure that out straight from the Q, but you can also figure out the mathematical value of delta G, and we'll see what happens there. Right, so delta G of the reaction equals delta G of the reaction at standard state plus RT ln Q. And so here we're at standard state, so delta G of reaction should equal to delta G at the standard state because we are at standard state. And so if you look at ln of Q right here, the gas is again going to be at 1 atmosphere, and it's just equal to hydrogen. So the ln of 1 is actually equal to 0. And so this whole part goes to 0. And so delta G equals delta G at standard state because we are at standard state. So it's this 8.959. Right, where did I get that number from? Got it from right here. Plugged it into there. The other part 0. And so it goes right there. Cool. So most of the time we're not at standard state. Most of the time gases aren't at 1 atmosphere. So let's take a look at what happens when we're not. But first, real quick, right, from this delta G being positive, you know it's non-spontaneous. And so that means it's spontaneous in the other direction. And so really what's happening now is the gas is condensing. So you can see these two, Q, K, and delta G, they both gave you the same prediction as they should. So let's take a look at a non-standard state, right? When delta G is not going to be equal to the delta G at standard state, right? So again, we're going to do the same example. Water evaporating into a gas. We're going to say we're still at 25 degrees Celsius. So that part we're keeping standard. But we're going to say it's a dry day. So you're, you live in California. So it's a dry day. So the amount of water as a gas is quite small, right? It's nowhere near that 1 atmosphere. It's 5 times 10 to the negative third. It's a 5. Can't draw on the edge of this thing for some reason. It's a 5. Anyways, so you can think in terms of equilibrium, or you can think in terms of Gibbs energy. And you'll see they'll say the same thing. Here, Q is actually less than K because our value of K we got from up here, which is this 0.0313. One zero. Cool. So Q is less than K, and so we know Q must grow to become K. And so the liquid is going to turn into a gas. You're going to get more products. It's going to evaporate, right? So will it evaporate on a dry day from our Q and K? Yes, we know it will. And then we can take a look at the delta G side of things. So again, the same equation as before. For Q now, we're going to go ahead and plug in this value right here. We're given Q. So we can just go ahead, plug it in for this Q part right here. This delta G at standard states we got from the previous problem. So it's this 8.59. We know that R is this 8.314. And then that temperature here, we're at 25 degrees Celsius. So you have to turn that into Kelvin. That should be 298 Kelvin. So go ahead, plug those numbers in. You'll get delta G is equal to 8.59 kilojoules per mole, plus the R is 8.314 joules per mole Kelvin. This is 298 Kelvin times the natural log of 0.005. So anytime you take the natural log of a number that's less than 1, it'll actually turn into a negative. So that part will go negative. So this part right here is actually going to give you a negative number. And then the other thing that you want to, these K's will cancel out. So they'll both be in joules per mole Kelvin, except this one right here, I think is in kilojoules, while this one right here is in joules. Make sure I pull that right, kilojoules per mole. So make sure you take that into account, that they're not the same unit. So this ends up being 8.59 kilojoules per mole minus 13 0.1 kilojoules per mole, right? And so then your delta G ends up being negative 4.5 kilojoules per mole, right? So I converted in between these two steps, right? Converted from joules to kilojoules. And so overall, this number right here is negative. So that tells you that it's spontaneous in the forward direction. So liquid is going to turn into gas, which is exactly what your equilibrium told you. So again, they're really the same concept. One of them is just the what, one of them is the why. Finally, let's take a look at what happens at equilibrium. Right, so you got water as a liquid, water as a gas, and this time we're told we're at equilibrium. K value, Kp here is 0.0313. And so we know we're at equilibrium. And so what that means is that Q is equal to K, which is in this case this 0.0193, and that there's then no net movement. Right, you still got water evaporating and water condensing, but they're happening at equal opposite rates, so there's no net movement. Right. And then you can think about delta G. Right, delta G at standard display plus RT. Right, got that equation right there. We can pull up the same number we've been using for right there, 8.314 in the R, 298 in the T, because we're still thinking about room temperature. And now we just go ahead and plug this value in right here. And then what you end up getting is that this is 8.59 kilojoules per mole. This value ends up being a plus negative 8.59 kilojoules per mole. And so delta G ends up being equal to 0, which means that there's no net movement. You're at equilibrium. Which is the exact same prediction that you got from comparing your Q's and your K's. And the reason they're given the same prediction again is the delta G is kind of the Y behind K. Say this reaction has a K of 5. Why does it have that K of 5? Well, it's because of the difference in Gibbs free energy of the two things, right? The products and the reactants, right? We know at equilibrium, Q equals K, and delta G is equal to 0. Rewrite this equation again. And see the mathematical relationship between the two, right? So we know delta G here is 0, so we can plug in 0 right there, and then we can reorganize the equation. The other thing we can do is we know that Q is equal to K, so we can switch this Q with a K. So what ends up happening is that you get delta G at standard state is equal to negative RT ln K. So you can see there's a direct relationship between delta G at standard states and K. Right, so you can calculate K for reactions if you have the delta G, or you can, do the reverse. There's also kind of qualitative questions you can ask. So there's different values of K. Remember, K is products over reactants. And so we generally think of K as equaling 1, being greater than 1, or being less than 1. While delta G of the reaction we think of being 0, being negative, or being positive. But let's take a look how they fit with one another. So when you have a K equal to 1? Well, since K is products over reactants, a K of 1 means you have equal amounts of products and reactants. And so if you plug in 1 here for K, and the natural log of 1 is going to be 0, so delta G thus ends up being 0, or vice versa. If delta G is 0, your K must be 1. And so the way you can kind of think about this is delta G is, remember, products over products minus reactants. Right, so it's the difference in energy here. So if you think about a graph, you have G and you have Q over here. And then let's say you have A over here, B over here. The delta G is 0, so they need to be on the same plane. And if you think about where the energy dip would be between them, it end up somewhere in the middle, right? And this lowest spot of energy, that's when Q is equal to K. So that's where you're going to end up. If you think about rolling a ball down either one of these hills, you're going to end up there at the bottom. Next up, we have a K greater than 1. Since products are on top, so that means you're going to have more product than reactant. So if you plug in a number greater than 1 here, the natural log of a number greater than 1 is positive. So this negative sign up here dominates, and so delta G becomes negative. And so kind of what you're thinking about, what does negative delta G mean? Well, it's delta G, so it's products minus reactants. And so if you have a negative number, that means that your products are in lower energy than your reactants. Think about kind of exothermic reaction, but we're not talking about exoendothermic, we're talking about delta G. So it'd be a situation like this. And if you think about kind of where the energy minima here would be, it'd be somewhere closer to B. And so you'd have more products than reactants. Final scenario, we've got a K less than 1, which means that we have more reactants than products, because reactants is the denominator. So more reactants than products. And then if you plug in a number that's less than 1 here, ln of a number less than 1 becomes a negative number. So these two negative numbers then cancel each other out, and you end up getting a positive for delta G here. So what does that mean? Again, if you kind of use the analogy of endo-exothermic, it means that your products are higher in delta G than they are than the reactant. So you'd have something like this, A, B. And then if you think about where kind of the energy minima would be here, somewhere it'd be closer to the reactants. So if you can find out the numerical values of delta G and K, and you can give approximate values. If your delta G is positive, then, or if your delta G at standard state is positive, then at standard states, you probably have more reactants than products, and you can go through the list, right? Be able to explain how to go from one to the other. Those little graphs shown here as well. So same thing I was drawing on that left-hand side, your relationship of between K and delta G. All right. If delta G is negative, less than 0, K is greater than 1. If delta G is greater than 0, K is less than 1. If delta G is equal to 0, your K is equal to 1. And again, it all goes back to the analogy in the first video, that if you kind of have some kind of hill, and then if you've got a ball, whether it's starting here or it's starting here, at the end of the day, where it's going to end up is at the bottom of the hill. And we define this hill height in terms of G. This would be kind of like reaction progress or something. Cool. Super important idea.